All right, what's up, peeps? Time for our second round of a two-prop z-test video here. So the first video, we went through kind of the whole process, just kind of how to get through a problem, write the hypotheses. That was the biggest new piece, the conditions. The math, we just took the stuff from the calculator and wrote our conclusion. So today we want to dive a little deeper into that math piece. Before we do that, a little special shout out there to Sarah and Xenia, who already, I know, did all of the work and just talked to me in office hours. So that's fantastic. Great job, ladies. Hopefully there's other people who did that. And then second special shout out, happy birthday, Xenia. So everyone text Xenia and say happy birthday. So let's do it. Let's hop right in. So here we go. So today we want to talk about the math, looking at something called p-hat pooled, and then a little review. We'll interpret our p-value, try to refresh our memories on what that means. So first up, here's our context. Same context we've been working with for our two proportion z intervals for our two proportion z test video, right? So if this is new to you, pause it, write this context down, familiarize yourself. All right, and these are the same question written twice, right? Snoring rate for people over 30 is the same thing as percent of people over 30 who snore. So we've just got the same question written using two different, or wording the question in two different ways. All right, so in the last video, we wrote the hypotheses, and one thing to keep in mind throughout this is when we wrote our hypotheses, we defined group 1 as the over 30 group and group 2 as the under 30 group. And so, right, our null was P1 equals P2. Our alternative was P1 greater than P2. If you flip the groups, that's fine, right? If you call 1 under and 2 over, totally fine, right? That's going to change your alternative, but everything we do moving forward will be done kind of with this, this key right here. So when we conducted our two-prop z-test, we produced this calculator output screen right here. All right, and so we already know that we can now, if I'm doing the exam, like I'm copying the screen, at least specifically, right, I need the name of the test or interval, I need my z-score, and I need my p-value. I may have already written these numbers down and these numbers if I create like that little 1-2 table we've looked at. But then the other thing is like this is not something we've seen before. So this number with this p-hat with no 1 or 2, that's not the p-hat for either specific sample. This is what's called p-hat pooled, and that's what we're going to start to look at and use today. So, right, we can write our conclusion based on this p-value. We know we're going to reject the null, but so today we want to look at the sketch of a normal model, visual representation of this p-value, and we also want to look at how is this z-score, this standardized test statistic, calculated. Now, the formula for the standardized test statistic is given on the AP exam formula sheet, as well as the standard errors, right? So if I jump ahead, here's that formula sheet. So we're given the formula for the standardized test statistic at the top. We just have to know that the standardized test statistic is a z or a t-score. And then down here, if I scroll down, here are all of our standard error formulas. We're talking two populations with percentages right now, so we're looking at this. Now, as we look at this box, this should jump out to you based on the null hypothesis that we used in the last video, right? So hopefully that's making you think about something, but I will say personally, like I never write my standard or error formula using this structure, right? So you could do everything without ever using this formula I just crossed out in green, right? It just so happens that if the P's, right, if these are the same number, then we can do some factoring and some algebra to rewrite this way, but not a huge deal going on there. So what I want you guys to do is to pause the video, not yet because I didn't explain the directions, unpause, and try to take a minute. I want you to sketch a shaded model, which we know we can use the draw feature of the calculator to help us with, but then I want you to try to show me the z-score formula, the test statistic formula, given that we have two p-hats. Remember the parameters based on our assumption and our null, and then our standard error formula, right, we just saw. So give it a pause and do that up. So I'm hoping our best guess in terms of the z-score formula, I'm hoping that we could produce something like this. So I'll kind of color code, right? So this red right here, that's our statistic situation, but we don't have one statistic, right? We have two. We don't have one sample, we have two. So we have two sample statistic, p-hat 1 and p-hat 2, two sample statistics, I caught that. p-hat 1 and p-hat 2, and we know, going back to the two prop z interval stuff, anytime we have two statistics, two values, we're going to focus on the difference. Since I have two p-hats, right, I'm going to subtract them. The parameter idea is always based on our null hypothesis. So this red, that's our sample difference. We could write that as 0.11, that's our sample difference. The parameter, that's our assumed difference. And in the 2-prop z-test video, we saw that we're always going to assume there's no difference between our two parameters. And so that's why this value right here is a 0. Before we get into the denominator, one other thing to point out is, so for us, we're using group 1 as the over 30 group and group 2 as the under 30 group. There's really no need for me to finish this. So if we flipped, if we wrote that, and if we labeled group 1 as under 30 and then group 2 as over 30, some things would change. So 1, the symbol in our alternative hypothesis would then be less than. And additionally, that would mean if we subtract in the other order, our z-score is going to become negative, and we'd be subtracting these in the opposite order. So if we subtracted under minus over, looking at all the blue stuff, we'd want to do 26% as our 1 and 37 as our 2, which would give us a negative difference here and would correspond to a negative z-score. So as you're setting up this formula, always pay attention to that. If your z-score is negative, then this difference right here better be negative. If your z-score is positive, then this difference right here better be positive. And then just keep in mind that everything we do is 1 minus 2. So group 1 minus group 2. That's why I like making that table, that T-chart, to summarize which one's which. So if we look at this, aside from all the blue stuff I just wrote down, so kind of jumping back to here, what's in this red box right now is pretty good. But I want you to think for a second. Think about the null hypothesis. So in our null hypothesis, we said in the null, P1 equals P2. Sorry for the sloppiness. And we saw we could also write that as P1 minus P2 equals 0, We assume there's literally 0 difference, No difference. But if you remember, we always assume the null is true. So for a 1 proportion z-test, our null said P equals some number. We had to use that number in our standard error formula and in our conditions because we had to stay consistent with that assumption. Now here, we're not assuming that P is any particular number, but we are assuming that the two P's are the same, We're assuming P1 and P2 are the same number, whether we look at it at the top or the bottom here. So this is a pretty good idea. And this is, in fact, what the standard error would look like for a confidence interval, because in a confidence interval, there's no assumption, no null hypothesis. But the problem is, right now, these numbers are not the same. We're not using the same P1 and P2, so we are contradicting this assumption that we made in the null. So we're going to have to change these values to stay consistent with our null hypothesis. How do we do that? We use what's called p-hat pooled. So for us, when we go to show our z-score formula, we're not going to use p-hat 1 and p-hat 2 in the denominator because we have to stay consistent with our null hypothesis. We're going to use p-hat pooled. So let me jump to the whiteboard here. So for us, when we go to calculate our z-score, we know our z-score is 2.8002. So how is this calculated? Our standardized test statistic, we start with stat minus parameter over standard error. And again, just to recap, the statistic, this is based on your sample. Now, we don't have one sample statistic. We have 2 of them. And anytime we have 2 things, 2 groups, 2 statistics, 2 parameters and stats, we want to focus on the difference. Our parameter over here, that's based on the null hypothesis. We're assuming the difference is 0. So black, that's our sample difference. Blue, that's our assumed difference. And so what we're going to do now for the denominator, for the standard error, this is still going to be our N1 and our N2. But for our standard error here, I can't use p hat 1 and p hat 2 because in my null hypothesis, right, I assumed P1 equals P2. And so that's the key that's behind all of this, right? We have to stay consistent with this assumption. So we have to use the same value for P hat 1 and P hat 2, or whatever. I'm sorry, for P1 and P2. And that number we're going to use is the P hat pool. So what we're going to use in this formula, P hat, it doesn't say P hat pooled on the calculator. It's the P hat with no subscript here. That was 0.35. And so this is going to be a 0.35 and then a 0.65. And this is going to be a 0.35 and a 0.65. And now I have not contradicted the original assumption I made in my null. Now I'm using the same P1 and same P2, and I'm staying consistent with this assumption. And so if I did out all of this work, which I am not going to do right now, but if I took some time to actually, do 0.11 divided by all this stuff under the radical, I would in fact get that z-score of 2.8002. So this blue box, this is how we can show the formula for our z-score in a 2-prop z-test. And so the only tweak is that we have to change this number to stay consistent with our null hypothesis. So that's what's up with p hat pooled. All right. So this relates to one of our conditions. See if you can think about which one. Give it a pause. Think about it for a minute. That's one nice thing that's about videos. You could take it as long as you want, right? Pause, think, come back to it, whatever. Notice, by the way, when I did write my formula, I just used this same structure here. I didn't really worry about this, right? But I could plug everything in using this setup, right? I could have written this kind of setup in the denominator as well, but whatever, it does the same thing. Hopefully you're thinking about that condition. Now I will say, right, we're trying to see if the samples are large enough. So this is how we checked the success failure condition for a confidence interval. And if you do that, that's like not that big of a deal. I wouldn't even really worry about it too much just based on some of the rubrics I've read. You would still get full credit for that. But if we truly are staying consistent with our null, P1 equals P2, we want to use that P hat pooled. We want to use the same number, right, to stay consistent with that assumption. And that's what you're seeing here. So that assumption, just like with a 1-prop z-test, affects two things: the calculation of the z-score and this one condition here. Although again, right, like this like isn't that big of a deal. I probably could have not had this slide and whatever, everything would have been fine. But right, we're always focused on, true deep understanding. And so this hopefully is logical. Yeah, these have to be the same number because we assumed P1 equals P2 in our null. So now the question is, what's up with p hat pool? Like, what is it? You like my pool picture? And that would be nice right now, right? Although now we'd all be in it alone. Hopefully someday we can see each other again when all this coronavirus stuff is over. So social distance, man, don't blow it. Anyways, if we pooled all our money, we'd put it all together, right? If we pool stuff, we put it together. That's what p hat pooled is. To calculate p hat pooled, we're gonna put a bunch of stuff together. So instead of treating it as two separate samples, we're gonna put everything together to form one group. So I'm gonna take the 811 people who were over 30 and add them to the 184 people who were under 30. So now I'm gonna have a total of 995 people. Now in the numerator, I want to look at the actual numbers of people who snored. So my denominator here in purple, that represents the total number of people we had, 995, no big deal. In the numerator, my X value of the over 30 people, 300 of them snored. That was 37% of the 811 people. Plus, in the under 30 group, 26% of the 184 snored, and that came out to be 48. And so our numerator here is going to be 348. And if in fact we do 348 out of 995, that is going to give us that p hat pooled of 0.35. So kind of recap, denominator here, we're looking at the total number of people who we surveyed, right? That's what's going on in the denominator. And then in the numerator up here, we've got the total number of people who snore. And that's how we're going to get p-hat pool. We're just going to pool everything together, all the snorers in both groups combined out of all the people in both groups combined. So that's where that 0.35 is coming from. Notice, if I jump back here, that formula is actually given on the formula sheet as well. There's our formula for p-hat pooled, right? And we can pull it off the calculator, so it's not a huge deal, but there is the formula for p-hat pooled. And there it is again. That's it. That's how we address the math, except one thing. Right about the sketch. So, understanding p-value. This hopefully now is review. So remember, p-value is a probability. It's a conditional probability. It's the probability we see some observed statistic, or in this case, an observed difference, a sample difference, if the null is true. All right, so it's a conditional probability. Since it's a probability, it's always going to be between 0 and 1. All right, nothing new there. Take a minute. Try to write a sentence interpreting the p-value in context. Pause. So the p-value is, I like to start, right, we're always assuming the null is true. So the p-value is, if the null is true, if there's really no difference in snoring rates, there's an incredibly small chance that we would see a sample difference like we saw of 0.11 or larger. But think about that. If P1 and P2 are the same, if the snoring rates are the same, it would be really unlikely to see a sample difference, right, this large or larger, right? We have 37 and 26%. That's where that's coming from. But like that happened, right? We took a sample, we surveyed 995 people, and we actually got these two percentages, 37 and 26%. But like, if the null were true, if the snoring rates were the same, this probably wouldn't have happened, but it did. If the null were true, this probably wouldn't happen, but it did happen. So that leads us to believe that null, probably not true. And that's kind of why a low p-value is going to lead us to reject the null, because if the null were true, there'd be a small probability we see a sample difference, right? Small probability we see a sample difference like this, but we did see this sample difference. This actually happened in real life. So we are now going to reject that original assumption and decide, hey, you know what? The snoring rate for group for the over 30 people probably had to actually be bigger, right? And that's all these bullets are walking through. So last thing, finish up here, that sketch, and this will kind of connect to what we just talked about. If we're going to sketch our normal model, we know that we could do this on the calculator. So there's a few ways we could do this here. So we've got our normal distribution. We could label this in terms of z-scores. I'll do that in blue. So if I label everything in terms of z-scores, this number in the middle is going to be 0. We got a z-score pretty far to the right of 2.008, right? So we had a z-score like of 2.008, and we're shading to the right. Now it's important to note two things. One, if you subtracted in the other order, you would have gotten a negative z-score, right? Because instead of doing 37 minus 26, you would have flipped it. The other thing that's important to note is this is not drawn to scale. So the p-value is represented by the size of the shaded region. So really, I should only be shading 0.003, right? Or 0.3% of this picture. But like, if I do that, then you guys like won't be able to see anything. So just kind of illustrate the point, I will make it a little smaller to better represent what's going on. But like if you get a p-value of 0.9, then you should be shading 90% of your picture. Here's what's going on if we label this in terms of percent of people who snore. I should say the difference in percents of people who snore, right? We have two samples, so we're always going to focus on the difference. So we would assume P1, right, equals P2. This number right here, that's based on my null hypothesis that P1 equals P2 or P1 minus P2 equals 0, right? Same thing. This would be 0.11, and that 0.11 is our sample percentage of 37% minus 26%. So there's two ways we could label. We could label in blue in terms of the z-scores. We could label in red in terms of differences in percents who snore. And again, what we're saying is, if it's true that the snoring rates are the same, it'd be pretty unlikely to get a difference in snoring rates of 11% or larger. But that actually happened. Probably wouldn't have happened if the null were true. So we're going to reject the null hypothesis and decide we think that one snoring rate, the over 30, is actually greater than the other, the under 30. And so that's our sketch. And you can think about things like, if we change the alternative to not equal to, how would that change this image? If we subtract in the other order I kind of mentioned, how would that change the image? Right, those are all questions we can consider and we'll see start to come up in our practice. All right, so that's it. Let's see, do I have anything else for you? Nah, do your homework. For real, do it. That dog says so. But also, this is my favorite quote, one of my favorites. It's one of the most true things you're going to read today. You're not great at stats because you were born that way. You get good at stats because you practice. So, practice. Peace out, homies.